In 2020, something unexpected happened. Supermarket shelves around the world began to empty. People stood in long lines before stores even opened. Shopping carts overflowed with one surprisingly ordinary product. Not food, not bottled water, not medicine, toilet paper. For the first time in modern history, millions of people realized just how essential it really was. Today, the average person uses around 100 rolls of toilet paper every year. That's billions of rolls produced worldwide. Yet almost nobody ever stops to ask a simple question: how is it actually made? Because behind every roll sitting quietly in your bathroom is one of the most fascinating recycling processes in modern manufacturing. A process that transforms yesterday's newspapers, old cardboard boxes, office documents, and discarded magazines into something clean enough to touch your skin. Today, we're taking you inside a factory where that transformation happens 24 hours a day, and once you see what happens inside, you'll never look at a roll of toilet paper the same way again. The journey doesn't begin with giant white rolls or massive paper machines. It begins with trash. Truck after truck arrives carrying enormous compressed bales of recycled paper collected from homes, offices, supermarkets, and recycling centers across the region. Each bale weighs close to half a metric ton, roughly the same weight as an adult horse. From the outside, they don't look very impressive, just giant cubes of tightly compressed waste. But hidden inside each one is an extraordinary mixture of fibers waiting for a second life. Newspapers, corrugated cardboard, office paper, magazines, packaging. Every bale tells a different story. No two are exactly alike. Some contain more cardboard, others are filled with office paper. Some include glossy magazines covered with colorful ink. The recipe constantly changes, but the destination never does. Every one of these forgotten materials is about to become something almost everyone uses every single day. Before the recycling process can even begin, every bale is inspected. Its weight is recorded, its moisture content is checked, and operators verify that it doesn't contain anything that could damage the machinery. Because recycling isn't as simple as throwing paper into a machine. Hidden inside these compressed blocks are things that were never supposed to be recycled. Plastic wrapping, metal wires, staples, adhesive tape, pieces of string. Sometimes even small objects accidentally thrown into recycling bins. One mistake here could damage equipment worth millions. So the inspection is as important as the recycling itself. Finally, the giant steel wires holding the bale together are cut. Almost immediately, the compressed paper begins expanding. It's almost like watching the material breathe for the first time. Layer after layer slowly pushes outward after spending weeks squeezed under enormous pressure. But that freedom lasts only a few moments, because the next machine waiting inside the factory has a single purpose: complete destruction. Welcome to the Hydra Pulpa. At first glance, it resembles an enormous steel tank. But in reality, it's one of the largest industrial blenders you will ever see. Inside, thousands of liters of water are heated to more than 70 degrees Celsius. Hidden beneath the surface sits a massive rotating impeller powerful enough to tear apart half a ton of paper in less than an hour. Imagine dropping an entire library into a giant washing machine. That's essentially what happens here. One bale after another is lifted overhead, then released into the hot water below. For a few seconds, the paper still keeps its familiar shape. You can recognize newspapers, pieces of cardboard, colorful magazine pages. But not for long. As the rotor begins spinning, a violent vortex forms inside the tank. Hot water rushes through every layer of compressed paper. The cardboard starts swelling. Magazine pages lose their glossy finish. Newspapers soften almost instantly. Then, everything begins falling apart. What once took months to print, read, fold, and recycle is reduced to pulp in a matter of minutes. The vortex grows stronger. Paper tears apart fiber by fiber. Every page disappears into a swirling gray mixture that looks more like oatmeal than paper. It's messy, it's noisy, and it's surprisingly beautiful. Because this is the exact moment old paper stops being paper. It becomes raw material once again. After nearly 45 minutes, the transformation is complete. There are no newspapers left, no cardboard, no magazines, only a thick gray suspension made mostly of water and tiny cellulose fibers. But despite appearances, this material is still far from clean. Mixed within the pulp are fragments of plastic, staples, glue, wax, sand, tiny pieces of glass, and millions of microscopic ink particles still clinging stubbornly to the fibers. If this pulp were turned into toilet paper now, it would be rough, gray, and completely unusable. Everything that does not belong has to disappear, and that is where the factory enters one of its most important stages, a place where physics does what brute force no longer can. Because in the next room, powerful screening systems and high-speed centrifugal cleaners will separate pure cellulose from everything else, one contaminant at a time. Only a few minutes ago, the material entering the factory looked like ordinary recycled paper. Now, it is nothing more than a thick gray slurry flowing through a network of massive steel pipes. At this point, the factory has achieved only one goal. It has destroyed the paper. But it has not created anything new yet, because hidden inside that gray mixture are thousands of contaminants that would make the final product completely unusable. Tiny pieces of plastic, staples, tape, glue, wax coatings, sand, glass, and, perhaps the biggest challenge of all, ink. Before this pulp can become soft, white toilet paper, it has to be cleaned more thoroughly than most people could ever imagine. The first stop is the screening room. This is where the factory begins separating useful cellulose fibers from everything that should not be there. The pulp enters a series of enormous cylindrical screens. At first glance, they do not look particularly complicated, but inside each one is a carefully engineered mesh designed to solve a very specific problem. The first screen catches the largest contaminants: plastic bags, packaging film, large pieces of tape, staples, bits of cardboard that never fully broke apart. Anything too large to continue is trapped immediately. The cellulose fibers, suspended in water, pass straight through. It is surprisingly similar to using a kitchen strainer, except this one processes thousands of liters every hour. As the unwanted material builds up, automatic cleaning systems activate. Powerful sprays continuously wash the screens, preventing them from clogging. The rejected waste falls into separate containers for disposal. Meanwhile, the pulp continues its journey. Cleaner than before, but still far from pure, because many contaminants are much smaller than the holes in the first screen. Some cannot even be seen with the naked eye. The pulp immediately enters a second screening stage. This time, the openings are dramatically smaller. Tiny flakes of plastic, fragments of adhesive, wax coatings from packaging, microscopic fibers from synthetic labels. Everything the first screen missed now has another chance to be removed. It is a process built around patience. Rather than trying to remove everything at once, the factory eliminates contaminants layer by layer, each stage preparing the pulp for the next. But not everything can be filtered. Some contaminants are simply too small. Others have almost the same size as the cellulose fibers themselves, so instead of using screens, the factory turns to something else: physics. Waiting just beyond the screening system are massive centrifugal cleaners. These machines do not rely on filters at all. Instead, they exploit one simple fact: not every material weighs the same. Inside each cleaner, the pulp is forced into a rapidly spinning cone. The rotation creates an incredibly powerful vortex, almost like a miniature tornado made of water. As everything spins at high speed, The heavier particles are thrown outward by centrifugal force. Sand, tiny stones, metal fragments, ground glass, anything dense enough is forced toward the outer walls before dropping harmlessly into a separate collection chamber. Meanwhile, the lighter cellulose fibers remain suspended near the center of the vortex. From there, they continue toward the next stage. No moving blades, no complicated robotics. Just pure physics doing the work. Watching the process is almost hypnotic. Thousands of liters of pulp race through dozens of cleaners simultaneously, each one removing only a tiny amount of contamination. But together, they make an enormous difference. Little by little, the pulp becomes smoother, cleaner, more uniform. The factory is not producing toilet paper yet, it is producing purity. Even after all of this, the pulp still does not look very impressive. It is no longer filled with solid debris, but its color remains a dull gray. The reason is simple. The large contaminants are gone, but the ink has not disappeared. Every newspaper headline, every magazine photograph, every printed advertisement, every office document, their pigments are still attached to millions of individual cellulose fibers, and unlike plastic or metal, ink cannot simply be filtered away. Because it is not floating freely in the water, it is chemically attached to the fibers themselves. Removing it requires an entirely different strategy. Imagine trying to remove permanent marker from a sheet of paper. No matter how much water you pour over it, the color stays behind. That's essentially the challenge facing the factory. Mechanical cleaning has reached its limit. The rest must be accomplished through chemistry and one surprisingly elegant trick: air. The pulp leaves the cleaning area through another maze of stainless steel pipelines. Its consistency is becoming more uniform with every meter it travels. Operators constantly monitor flow rates, fiber concentration, pressure, and temperature. Because even a small imbalance here can affect everything downstream. Too much fiber, and later processes become inefficient. Too much water, and the chemicals won't work properly. Every variable matters. Every adjustment is measured in fractions. As the gray pulp flows toward the next building, it almost looks alive. Slowly swirling through transparent inspection pipes, you can still see the dark tint left behind by millions of microscopic ink particles. It's the final reminder of everything this material used to be. Newspapers, magazines, cardboard boxes, office documents. All of those previous lives are still visible, not in their shape, but in their color. That color has to disappear, because no one expects toilet paper to be gray, and making it white requires one of the cleverest processes in the entire factory. Not powerful blades, not hotter water, not stronger filters. Just millions upon millions of microscopic air bubbles, each one smaller than a pinhead, because in the next stage, those tiny bubbles will accomplish something no machine has managed to do so far. They'll strip the ink away, one particle at a time. The pulp has survived grinders, screens, and powerful centrifugal cleaners. Most of the solid contaminants are gone. No more plastic, no more staples, no more glass, no more sand. But if you looked inside the pipes, you'd still never mistake it for clean paper. The color tells the whole story. It's still gray. Every newspaper headline, every magazine advertisement, every office document has left something behind. Not the paper itself, but the ink. And unlike the larger contaminants, ink is almost impossible to remove mechanically. It's attached directly to the cellulose fibers. To separate the two, the factory uses one of the most ingenious techniques in the recycling industry. Not with blades, not with filters, but with air. Welcome to the de-inking department. At first glance, the equipment looks surprisingly simple. A series of tall flotation tanks connected by massive pipelines. Inside, the pulp moves slowly through the water. It does not look dramatic, But what is happening beneath the surface is one of the most sophisticated chemical processes in the entire factory. Before the pulp enters the tanks, engineers carefully add a precise mixture of chemicals, surfactants, dispersing agents, and small amounts of soap-like compounds. Their job is not to bleach the paper. It is to change the behavior of the ink. Normally, ink clings stubbornly to cellulose fibers. These chemicals weaken that bond, making it possible for the ink to detach. But chemistry alone is not enough. The factory still needs something to carry those ink particles away. That is where millions of microscopic air bubbles come in. Compressed air is injected into the bottom of the flotation tanks. Instantly, millions of bubbles begin rising toward the surface. Each one is incredibly small, almost invisible, yet together, they perform a task no filter could ever accomplish. Ink has an unusual property. It repels water, but it readily sticks to air. As each tiny bubble rises through the pulp, microscopic ink particles attach themselves to its surface, one by one, millions of times every second. It is almost like watching countless tiny magnets pulling contamination upward, except nothing is magnetic. It is simply physics and chemistry working together. As more bubbles reach the surface, something remarkable begins to happen. A thick black foam slowly forms across the top of the tank. It does not look pleasant. In fact, it is one of the dirtiest substances anywhere in the factory. But that is exactly what makes it so satisfying to watch. Every bit of dark foam represents contamination that has been removed from the fibers below. Thousands of newspapers, countless magazines, years of printed ink, all concentrated into a layer of floating waste. Below that foam, the pulp is already becoming noticeably lighter. Large rotating paddles slowly sweep across the surface. With every pass, they skim away the dark foam, carrying it into separate waste channels. The process never stops. Fresh bubbles continue rising. More ink reaches the surface. More foam is removed. It is a continuous cycle, simple in appearance, remarkably effective in practice. Watching the tanks from above, you can actually see the transformation happening. One end is noticeably darker, the other much cleaner. But one flotation stage is not enough. Some ink particles cling more tightly than others, so the pulp enters a second flotation tank. The entire process repeats itself. More chemicals, more microscopic bubbles, more black foam, and even cleaner fibers. Each pass removes another fraction of contamination. Little by little, gray becomes pale gray. Then, a light cream color begins to appear. For the first time since entering the factory, the material starts resembling fresh paper pulp instead of recycled waste. Even after flotation, the job isn't completely finished. The pulp now moves through several washing stages. Large volumes of clean water flush away the smallest remaining traces of detached ink, residual chemicals, and microscopic impurities. Every wash makes the fibers just a little cleaner, a little brighter, a little purer. The water leaving these systems looks dramatically darker than the water entering them. That's because it's carrying away the last visible reminders of the paper's previous life. It's remarkable to think that only a short time ago, these same fibers were covered in colorful advertisements, black newspaper print, and glossy magazine photos. Now, most of that history has literally been washed away. By the end of the washing process, the pulp has changed completely. Gone is the thick gray slurry from the hydropulper. What remains is a smooth, cream-colored suspension of almost pure cellulose. If you didn't know where it came from, you'd never guess it had once been made from discarded newspapers and cardboard boxes. But despite its dramatic transformation, the factory isn't finished yet, because consumers don't expect toilet paper to be cream-colored. They expect brilliant white. Achieving that final color requires another carefully controlled chemical process, one that must be powerful enough to brighten the fibers, yet gentle enough to preserve their strength. Years ago, many paper mills relied on chlorine-based bleaching systems. They were effective, but they also created serious environmental concerns. Modern factories use a much more advanced approach. Here, the primary whitening agent is hydrogen peroxide, the same chemical family used in common antiseptic solutions, only in carefully controlled industrial concentrations, inside enormous mixing tanks. The peroxide begins reacting with the remaining natural compounds still trapped inside the cellulose. One of the most important is lignin. This substance is naturally present in wood fibers and is largely responsible for paper turning yellow over time. As the peroxide breaks it down, the fibers become brighter, cleaner, whiter. Sometimes ozone is introduced as a complementary treatment, helping achieve an even more consistent color without relying on chlorine. The result is a process that's both highly effective and significantly more environmentally friendly than older bleaching methods. By the time the chemical reactions are complete, the transformation is extraordinary. Just a few hours ago, these fibers were trapped inside dirty newspapers and worn-out cardboard. Now they're bright white, soft, clean, almost impossible to distinguish from virgin paper pulp. But color alone doesn't make great toilet paper. The fibers themselves still need to be carefully engineered, because if they're too long, the paper will feel rough. Too short, and it could fall apart the moment you use it. The next machines will solve that problem with incredible precision, preparing every single fiber for the moment it finally becomes paper once again. By this point, the transformation is almost unbelievable. Old newspapers, cardboard boxes, office paper, and glossy magazines have all disappeared. Not physically, but chemically. What remains is a bright white suspension made almost entirely of purified cellulose fibers. It looks clean. It feels smooth. But there's one surprising fact. It still isn't paper. In fact, it's almost entirely water. More than 99% of the mixture flowing through the pipes is liquid. The actual fibers that will become toilet paper represent less than 1% of the total volume. Imagine filling a swimming pool and hiding the paper inside it. That's essentially what the factory is about to work with. The challenge now isn't cleaning the fibers anymore. It's removing almost every drop of water without breaking the incredibly delicate web they're about to form. The pulp travels toward the largest machine in the entire factory, stretching for dozens of meters, towering above the production floor. This single machine performs what almost feels like an industrial magic trick. It turns water into paper. Around the world, paper engineers simply call it the paper machine. But there's nothing simple about it. Every hour, it transforms thousands of liters of watery pulp into one continuous sheet that can stretch for kilometers without ever stopping. If this machine shuts down unexpectedly, the entire factory stops with it. Everything begins at the head box. This enormous chamber has one critical job: to spread the pulp across the machine with absolute precision. The mixture does not pour onto the conveyor like a bucket of water. Instead, it exits through a narrow opening as a perfectly controlled curtain. Every millimeter receives exactly the same amount of fiber. Too much pulp on one side, and the finished paper becomes thicker. Too little, and weak spots begin to appear. Something as small as a slight imbalance here could create thousands of defective rolls later. That is why computers constantly monitor the flow, making microscopic corrections hundreds of times every second. The thin curtain of pulp lands gently on a moving wire mesh. At first, it barely looks like anything, just cloudy water spreading across a conveyor, but something extraordinary is already happening. Gravity immediately begins pulling the water downward through the mesh. The cellulose fibers, too large to pass through, remain on the surface. Tiny by tiny, they begin touching one another, interlocking naturally, forming an incredibly delicate web. It is so thin, that light can almost pass straight through it. Yet for the first time since entering the factory, it can officially be called paper. Of course, this newborn sheet is still incredibly fragile. Pick it up now, and it would fall apart instantly. Almost all of the water is still trapped inside, so the machine introduces the next stage, vacuum. Beneath the moving wire, powerful vacuum boxes begin sucking water through the underside of the sheet. You cannot actually see the suction happening, but you can see its effects. Every meter the paper travels, it becomes slightly drier, slightly stronger. The fibers lock together more tightly. The once transparent web slowly turns opaque. The transformation happens in seconds, yet it is based entirely on something we use every day: air pressure. Once enough water has been removed, the fragile sheet reaches a series of massive press rollers. These are not ordinary rollers. Each pair applies enormous pressure across the entire width of the paper. As the sheet passes between them, water is literally squeezed out. Imagine pressing a soaked sponge between your hands. Now imagine doing that continuously, thousands of times every hour. That is exactly what these rollers accomplish. With every pass, the paper becomes denser, stronger, more stable. Its surface smooths out. Its structure becomes more uniform. For the first time, it begins to resemble the material we recognize as paper. But even after all that pressing, there's still too much moisture left. And that's where one of the factory's most impressive machines takes over. The Yankee dryer. Standing several stories tall, this enormous polished steel cylinder can measure up to 5 meters in diameter. Inside, pressurized steam heats the metal surface to well over 100 degrees Celsius. The paper is gently pressed against the cylinder, almost hugging the hot steel as it travels around its surface. Heat begins flowing directly into the sheet. Water evaporates almost instantly. Above the cylinder, a massive hood blows streams of hot air across the paper. The two heating systems work together. Heat from below, hot air from above, removing moisture at incredible speed. By the time the sheet completes its journey around the cylinder, it's almost completely dry. But something extraordinary is still missing: softness. Without it, the paper would feel stiff, rough, almost like writing paper. Everything changes in a single instant. At the very end of the Yankee dryer, a razor-sharp steel blade waits against the rotating cylinder. This is the creeping blade, arguably the most important tool in the entire factory. As the paper reaches the blade, it's gently scraped away from the hot steel surface. The movement is incredibly small, barely visible, yet under a microscope, the paper changes completely. Millions of microscopic wrinkles instantly form across the sheet. These tiny folds trap pockets of air between the fibers. Those invisible air pockets are exactly what create the softness we associate with toilet paper. Without creeping, toilet paper wouldn't feel soft. It wouldn't stretch properly, and it certainly wouldn't be comfortable to use. The comfort you've experienced your entire life is created in less than a second. As the freshly creeped paper leaves the dryer, it almost floats through the factory. Bright white, soft, flexible, and remarkably light. Just a few hours ago, this same material existed as dirty newspapers soaking inside a giant steel tank. Now, it's a continuous ribbon of premium tissue paper stretching hundreds of meters across the production line. The impossible transformation is nearly complete. But before this paper can become the familiar rolls found in every supermarket, it first has to become something much bigger. Because the next machine won't make toilet paper rolls. It will create gigantic parent rolls, each one containing enough paper to produce thousands of them. The sheet leaving the paper machine already looks exactly like toilet paper. It is white, it is soft, it is flexible. But there is one obvious problem. It is only a single, endless ribbon. No perforations, no cardboard tube, no individual rolls. Before any of that can happen, The factory has to do something surprisingly simple. It has to roll the paper back up. Only this time, on a scale that is almost impossible to imagine. As the freshly dried tissue leaves the Yankee dryer, it travels at hundreds of meters per minute toward the rewinder. There, an empty steel core begins waiting for its first layer of paper. At first, it looks almost insignificant, just a metal cylinder slowly spinning in place. Then the paper touches it. The first wrap locks into position. Another follows, then another. Within seconds, the roll begins to grow. Layer after layer, the tissue wraps around itself with astonishing precision. Every revolution adds another microscopic layer. Every minute adds hundreds more. Unlike a household roll, which contains only a few dozen meters of paper, this parent roll will eventually hold several kilometers of continuous tissue, enough to manufacture thousands of individual rolls. Watching it grow is strangely mesmerizing. The diameter increases almost imperceptibly, 1 meter, then 1.5, eventually more than 2 meters across. Standing beside it, the scale becomes obvious. An operator looks tiny compared to the massive white cylinder. What appears soft and lightweight suddenly becomes incredibly heavy, despite being made almost entirely of air-filled tissue. A fully wound parent roll can weigh several tons. Yet every layer has been wound with exactly the same tension. Too loose, and the roll collapses under its own weight. Too tight, and the paper could wrinkle or tear before it ever reaches the next machine. Maintaining that perfect balance is one of the rewinder's most important jobs. Sophisticated sensors constantly measure the roll's diameter, speed, and winding pressure. As the roll grows larger, the machine automatically adjusts every parameter. Because the outer layers travel farther with each rotation than the inner ones, even a tiny error would become thousands of meters of wasted paper. Eventually, the parent roll reaches its final size. A cutting system separates it from the endless paper web behind it. For the first time since leaving the paper machine, the paper stops moving. The enormous white cylinder is gently lifted away using specialized lifting equipment designed specifically for rolls of this size. From above, the warehouse begins to fill with giant white drums lined up in perfect rows. They almost resemble enormous marshmallows, or oversized wheels waiting to be installed on some impossible machine. Each one represents hours of continuous production. Each one contains enough tissue to supply thousands of homes. But surprisingly, not every roll earns the right to continue. Before entering the converting department, every parent roll must pass a series of quality inspections. Because if there is a defect hidden somewhere inside, it will be multiplied thousands of times during conversion. The first inspection measures thickness. Laser sensors scan across the width of the roll, looking for even the smallest variation. A sheet that is only fractions of a millimeter thicker in one area could create problems later when the paper is folded, embossed, or perforated. Consistency is everything. Next comes strength testing. Small samples are removed from the roll and stretched under carefully controlled conditions. The paper must be strong enough to survive high-speed manufacturing, yet delicate enough to tear easily when someone pulls a sheet at home. Finding that balance is not easy. Too much strength, and users struggle to separate each sheet. Too little, and the paper breaks while still inside the dispenser. Softness is tested as well. Some measurements are performed by precision instruments capable of detecting microscopic differences in texture. But in many factories, experienced quality inspectors still perform one surprisingly low-tech test. They touch it. Years of experience allow trained operators to detect subtle differences that even sophisticated machines sometimes miss. A slightly rough surface, an unusual stiffness, a change in the creeping pattern. Human skin remains one of the most sensitive quality control tools ever developed. If something does not feel right, the roll does not continue. Finally, color and appearance are inspected. The tissue must be uniformly bright, free from spots, free from holes, free from wrinkles. Even the smallest defect can cause problems once the paper begins moving at full production speed. Only after passing every inspection is the parent roll officially approved. From this point forward, its journey accelerates dramatically, because everything you have seen so far has actually been the slow part of the process. Creating the paper takes time. Turning it into toilet paper happens astonishingly fast. One by one, the giant rolls leave the warehouse and travel toward the converting hall. This is where the factory changes personality. The slow, careful precision of papermaking gives way to incredible speed. Conveyor systems position the massive rolls beside machines capable of processing tissue at more than 600 meters every minute. That is faster than many high-speed trains. In just a few moments, those enormous cylinders will begin disappearing, not because they are being recycled again, but because they will be transformed into something everyone instantly recognizes. Thousands upon thousands of perfectly finished toilet paper rolls, produced so quickly that the human eye can barely follow the process. The parent rolls are finally ready. Each one contains kilometers of perfectly engineered tissue. Soft, bright white, strong enough to survive manufacturing, gentle enough for everyday use. But despite everything the factory has accomplished, they're still nothing more than giant cylinders of paper. No perforations, no embossed texture, no cardboard core, no individual rolls. That transformation happens here, inside the converting hall, the fastest department in the entire factory. The moment a parent roll is loaded onto the converting machine, everything changes. The calm rhythm of the paper machine disappears. Now, everything moves at breathtaking speed. The enormous roll begins spinning. Slowly at first, then faster, and faster still. Within seconds, the tissue is racing through the machine at more than 600 meters every minute. That is nearly 10 meters every second. Blink, and several household rolls have already been produced. For premium toilet paper, one sheet is not enough. Most brands use 2 or even 3 layers. The factory creates these by feeding multiple parent rolls into the converter simultaneously. Each roll unwinds with incredible precision. The sheets travel side by side, perfectly synchronized. If one layer moved even slightly faster than the other, the finished roll would wrinkle almost immediately. Laser sensors constantly monitor their alignment. Tiny motors make microscopic corrections hundreds of times every second. To us, the paper looks like it is moving effortlessly. To the machine, every millimeter matters. The separate layers finally meet. Instead of being glued across their entire surface, only microscopic bonding points are applied. Tiny dots of adhesive hold the layers together while allowing small pockets of air to remain trapped between them. Those invisible air pockets make a remarkable difference. They increase softness, improve insulation, and help the paper absorb moisture much more efficiently. The result feels thicker without actually using much more material. It's clever engineering hidden inside something most people never think about. Next comes one of the paper's most recognizable features, its texture. Every roll you've ever used is covered in tiny patterns, diamonds, circles, flowers, geometric shapes. Most people assume they're simply decorative. They're not. The paper now passes between massive engraved steel rollers. This process is called embossing. As enormous pressure is applied, the engraved pattern is pressed directly into the tissue. Under a microscope, the transformation is extraordinary. The embossed pattern creates thousands of tiny pockets filled with air. These pockets increase the paper's thickness without adding extra fiber. More importantly, they dramatically improve absorbency. When liquid touches the paper, those microscopic cavities help pull moisture inside through capillary action. The result is a product that's both softer and far more effective. Something as simple as a tiny diamond pattern is actually the result of careful engineering. Almost immediately afterward, another set of rollers begins creating the perforation lines. These tiny cuts determine where each individual sheet will separate. It sounds simple. In reality, it's one of the most carefully calibrated operations in the factory. If the cuts are too deep, the roll could fall apart while it's still being packaged. Too shallow, and people would struggle to tear off a single sheet. The machine must strike the perfect balance, strong enough to survive transportation, weak enough to separate cleanly with one hand. Every perforation is spaced with incredible precision, hundreds of times every minute. Thousands of times every hour, day and night, without interruption. Now comes the moment when the product finally begins looking familiar. Cardboard tubes manufactured separately from recycled paper enter the machine at exactly the right moment. The tissue wraps tightly around each core while maintaining perfectly controlled tension. Layer after layer, the familiar toilet paper roll begins taking shape. The machine never slows down. Every movement is synchronized. Wrapping, bonding, perforating. Everything happens simultaneously, at full speed. It's less like watching a factory and more like watching a perfectly choreographed mechanical performance. Once the desired diameter has been reached, a tiny line of adhesive seals the loose end of the paper. The roll is now complete, almost, because what leaves the winding station isn't a single toilet paper roll. It's something manufacturers call a log. Imagine placing dozens of finished rolls side by side without cutting them apart. That's exactly what it looks like. A long white cylinder, several meters in length, smooth, perfectly wound, waiting for one final operation. The logs travel toward high-speed circular saws. These blades rotate at incredible speed, yet despite their power, their cuts are astonishingly precise. Each pass slices the long log into perfectly identical rolls. Every produces another finished product. One after another, after another. In just seconds, a single log becomes dozens of individual rolls. The transformation happens so quickly that it's almost impossible for the eye to follow. One moment, there's a continuous cylinder. The next, an endless stream of perfectly finished toilet paper rolls flows down the conveyor, thousands every hour, without the machines ever stopping. But before a single roll earns its place inside a package, the factory performs one final inspection, because even at these incredible speeds, quality still comes first. High-speed cameras examine every roll as it passes. Powerful software searches for wrinkles, tears, incorrect diameters, misaligned embossing, or damaged edges. If even the smallest defect is detected, a burst of compressed air instantly ejects that roll from the production line. It all happens in a fraction of a second, so quickly. Most people watching the conveyor never even notice. By the time the rolls reach the end of the line, only the perfect ones remain, ready for the final stage of their journey. Because the next time you see them, they'll no longer look like factory products. They'll look exactly the way they do on the supermarket shelf, wrapped, branded, and ready to go home with millions of customers. The hardest part is over. The paper has been recycled, cleaned, whitened, pressed, dried, embossed, perforated, and into perfectly finished rolls. But surprisingly, the factory still is not done, because making a great product means nothing if customers never receive it in perfect condition. As thousands of rolls stream down the conveyor belts, one final round of quality checks begins. Some inspections are performed automatically, others still rely on human experience. High-speed cameras examine every single roll from multiple angles. Powerful software measures the diameter, checks the embossed pattern, looks for torn edges, and confirms that every perforation is perfectly aligned. Nothing escapes these cameras. Even defects too small for the human eye can be detected. If a roll fails inspection, it never reaches the customer. A precisely timed jet of compressed air instantly knocks it off the conveyor. 1 second it is part of the production line. The next, it is gone. The machine never slows down. It simply keeps producing. But technology still has limits. That is why trained quality inspectors continue performing manual tests throughout the day. They pull individual sheets. They check how easily the paper tears. They feel the softness between their fingers. They squeeze it, stretch it, even smell it. Because despite all the sensors and automation, human touch remains one of the best quality control tools ever created. If something feels wrong, customers will notice it too. Once approved, the rolls continue toward the packaging area. Until now, they have looked exactly the same. Plain white, unbranded, almost anonymous. In just a few seconds, that changes completely. The rolls are carefully grouped together. 4, 6, 12, or even 24 at a time, depending on the product being manufactured. Above the conveyor, a continuous sleeve of printed plastic film waits to wrap around them. The packaging slides smoothly into place. Heat sealing bars close both ends almost instantly. In less than a second, a loose group of rolls has become a finished retail package. The transformation is surprisingly satisfying to watch. One moment, it is just paper. The next, it is the exact product you will recognize on a supermarket shelf. Every package receives important information before leaving the line. Product details, batch numbers, manufacturing dates, barcodes, everything needed to trace that package back through the factory if necessary. That level of traceability is essential. If a quality issue is ever discovered, manufacturers can identify exactly when the product was made, which machines produced it, and even which batch of recycled paper was used. It's a level of precision most customers never see, but it's happening behind every package they buy. The finished packs continue toward large robotic palletizers. Instead of human workers stacking products one by one, industrial robots take over. Their movements are smooth, fast, and incredibly precise. One package after another, they build perfectly stable pallets, layer by layer. Every stack follows an exact pattern designed to maximize stability during transportation. Once complete, the entire pallet is wrapped in protective stretch film. Now it's ready for shipping. From there, forklifts carry the finished pallets into the warehouse. Thousands of rolls wait quietly in neat rows. Just hours ago, this space was filled with giant bales of discarded paper arriving for recycling. Now, it's filled with finished products ready to leave. The transformation is complete. What entered the factory as waste leaves as something millions of people depend on every single day. Before sunrise, loading docks come to life. Trucks begin backing into position. One pallet after another is carefully loaded inside. Each truck carries tens of thousands of rolls destined for supermarkets, convenience stores, hotels, hospitals, schools, and homes across the region. Within hours, those trucks will disappear onto highways in every direction. Most customers will never know where their toilet paper came from. They'll simply grab a package from a shelf, place it in their shopping cart, and head home, without realizing the incredible journey hidden inside every roll. Think about everything you've just seen. It began as old newspapers, cardboard boxes, office documents, and magazines that most people considered worthless. Those materials were shredded, washed, cleaned, separated, whitened, pressed, dried, embossed, converted, inspected, and packaged, all so they could begin a second life. It's one of the most impressive examples of modern recycling in action, a process that quietly saves enormous amounts of raw materials, reduces waste, and transforms yesterday's trash into one of the most essential products we use every day. The next time you reach for a roll of toilet paper, you'll know you're holding far more than just paper. You are holding the result of thousands of engineering decisions, remarkable chemistry, precision manufacturing, and one extraordinary recycling journey. If you enjoyed discovering what really happens before every roll reaches your bathroom, you are in the right place. Here at Source Code, we uncover the hidden processes behind the products, industries, and technologies that shape our everyday lives. If you have not already, make sure to subscribe and turn on notifications so you never miss the next journey behind the scenes. Thanks for watching, and we will see you in the next episode of Source Code.